Welcome, welcome, welcome everybody to the 2016-2017 school year at Elk River High School. This will be one for the books. This is a very interesting 2 weeks of school that we have going on here. But I'm going to be very excited to meet you all in class. Pre-calculus is such a fun course to teach. There are so many topics that we cover. A lot of them will feel like they are things that you already know, things that we just build on, pieces that you already know of. And then there are going to be a lot of pieces where it might feel like, hey, this is the first time I've ever seen this. So pre-calculus is about exposing you to all the math that you could use wherever you are able to go after pre-calculus. Lots of you will go to calculus. Some of you will go to stats. There's just a lot of different places people can go, and we want to prepare you for all of those places. So chapter P is called our chapter with prerequisite skills. These are the things you have to be able to do, and to be successful in pre-calculus, these things should be really basic to you. Now, I say that, and then we're going to have some new notation. So it's your understanding that is supposed to be really basic to you. But there will be a few new pieces in here. So notice the caption underneath this picture says large distances are measured in light years. The distance light travels in 1 year. The reason we have to do that is because they're so far away. To write those numbers the way that we normally would, which would be in terms of miles or kilometers, we would have so many zeros, we would just get lost in it. So astronomers use the speed of light, which is approximately 186,000 miles per second, to approximate distances between planets. And as it says, when we get to page 35, we're going to see some examples, and we're going to do some writing. And obviously, scientific notation becomes a part of that as we try to figure out how do we write these really large numbers. All right, as it says here, you should be highlighting the topics below as they're taught to you in class. So as we discuss these, and at the end of the day, I'd really like you to think about writing summaries about what you've learned for the day. You would want to go ahead and grab yourself a highlighter and say, oh yeah, this was what we did today. I know that now. You know, basic properties of real numbers, that's already done. And then go ahead and do that each day as we go through the material so that you can see at the end, yep, we've really covered all of this stuff. So basic properties of real numbers, absolute value, distance formula, midpoint formula, equations of circles, slope, standard equations for lines, applications involving linear equations. That, of course, means we're going to start seeing some word problems. You know, that's what all this is about, being able to apply this to the things that you need in real life. And then solving equations and solving inequalities by algebraic and graphical methods. So that's where we're going to go as we work through chapter P. We're also going to deal with some of the appendices in the back of the book as we try to make sure that we build up all the skills that you need as we go through pre-calculus. Pre-calc section P1 is number systems, notation, and properties. Now, like I said, we're going to talk about the notation. We're going to get some new notation. Basically, we want to simplify the notation as much as possible, and you'll see that as we go through all of this. So you should be able to, here are the objectives. Identify subsets of the real number system. We'll get to that one today. Correctly use set builder and interval notation. That's going to be the focus of quite a bit of our day one lesson here. Correctly use the basic properties of algebra. Well, we're going to have to hang off day 2 for a lot of that. And for the rest of this, which would be correctly use the properties of exponents, simplify algebraic expressions, and convert between scientific notation and decimal form. So for today, what we'll be doing is definitely going through these two. Those will be objectives that we can set for ourselves. You know, when we get done, you want to ask yourself, could I identify subsets of the real number system? Could I correctly use set builder and interval notation? So let's jump right in and take a peek at what we're talking about and what kind of notation we're going to use here. These are the number systems. Now, I always think of in terms of the number systems as being a basic story of all humanity, you know, all the things that we've encountered from the time there were cavemen, you know. And to me, it just seems that the natural numbers is a natural place to start, because that would have been the first time that somebody wanted to figure out how many cobs of corn do we have to feed everybody. And you just started counting. So you counted 1, 2, 3, 4, etc. So you're starting with 1, and you're going on forever just using those counting numbers, the natural numbers. We're going to go ahead and use an N to stand for the natural numbers. So now people are able to start trading with each other, you know, and they start to keep a log of how much they're giving somebody. And at some point, somebody pays off their whole bill, and we have to have a number to represent that. So that's where 0 came in. So that included the natural numbers, 1, 2, 3, 4, on up forever. But we also needed to have that 0 in there as we tried to keep track of how much we owe or what the result of a trade was. And if it meant that you were even Steven, you needed a 0 to represent that. Then there would have been some years when the farmer next to you had a bad year. And they'd come over and they'd just beg you, please, you know, I've got to get my family through the winter here. Oh, that's interesting, isn't it? So now what we do is we try to say, okay, I really wish I could, but in my book, I have to put a number to represent what I'm giving you. And that would have involved putting some negative numbers in those places. So we would go ahead and now have a number system which would go off in both directions. So -3, -2, -1, but remember that can go to the left forever. 0, 1, 2, 3, that can go to the right forever. And those are the integers. And so we're going to use a Z to stand for those integers. So now we have the integers. And every once in a while, an instance will pop up when you don't have a full bushel of apples to give to somebody. You only have a partial bushel of apples to give to somebody. And that's where fractions came from, where we're trying to say, no, we're not going to use the whole thing. We're just going to use a portion of it. And we're going to use the letter Q to stand for that. But rational just means any number that we could write as a ratio, and ratio in math is a fraction. So notice all of our integers, those are rational, because if we take -3 and we put it over 1, well, then that's going to be a rational number. So the natural numbers, whole numbers, and integers are all included in the rational numbers because they can be written as a fraction. And then we have the real numbers. And the real numbers are just that. Basically, these are all the numbers that you knew up until Algebra 2, because we didn't talk to you at all. And real number symbol there is an R with an extra line on the left-hand side of it. So it's like 2 lines on the left and then a fancy R. So those are the real numbers. Well, those are the natural, the whole, the integers, and the rational numbers. But notice another part of this Venn diagram is these irrational numbers. And those irrational numbers, we're going to use an I to symbolize those. And those numbers are numbers that if you put them into your calculator, you're going to see that there is no pattern to them, and there's no repetition, and there wouldn't be a way to write them as a fraction. So irrational numbers are like the square root of 2. If you punch that into your calculator, you'll see there's no repetition. It doesn't stop. Our calculator stops it. Our calculator rounds at that 10 digits because it only has so much room on the screen to give us those numbers, but they continue on forever. Probably the most famous of the irrational numbers would be pi. That one they have gotten to the 10 millionth digit and there still is no pattern. Now, you'll notice that all of these numbers seem to be inside this number system called the complex numbers. We're going to go ahead and use a C to stand for the complex number system. So our largest subset that we see there is the real numbers. The real numbers are definitely in the complex number system, but so are the imaginary numbers that you learned last year in Algebra 2. And those imaginary numbers, we're going to go ahead and use an M to stand for the imaginary numbers. And we have pure imaginary numbers, which would be a number such as 2i. And we also have our complex numbers, which are imaginary numbers, but they have a real number part. These were the things that you had to write as a plus bi last year, so 3 minus 2i. That would be an imaginary number. So we'd have a pure imaginary number in 2i, but 3 minus 2i is still considered an imaginary number. So our complex number system is made up of two rather large subsets made up of the real number system and the imaginary number system all put together. So this is how we would represent all the numbers that you have learned up to this point in your mathematics education. Note, unless specified, we're just going to work with the real numbers this year. There are times when we talk about the imaginary, but mostly what we want to do in pre-calculus is to be able to apply these to real life. And it's pretty rare that you're going to end up with something imaginary showing up in real life situations. While I'm thinking of it here, whenever I uncover a box, you have that box in your notes, and you need to fill that in. So as we get to this point where I'm uncovering real numbers, you should be writing everything along with me, obviously, as you're taking notes, but you should also be filling in those boxes. Now, we start talking about some notation here. The sets that we had up there, the sets that are inside other sets, are called subsets. The natural numbers are a subset of the whole number because they fit inside the whole numbers. The irrational numbers are a subset of the real numbers because they fit inside the big box, I guess we could call it, that we have real numbers in. So a Venn diagram is a great way to show what set is inside another set. Notice if I asked you, is the imaginary number set, the set of imaginary numbers, is that a subset of the natural numbers? Your answer would be no. No, that's not inside the natural numbers. Those are two totally different sets. So it's not a subset. So there could be several questions that we could give you on is the integers, or are the integers, are they a subset of the irrational numbers? And questions like that would get you to think of, wait a minute, was that inside? Are the irrational numbers inside that set? And the answer in that case would be no. So sets that are contained within other sets are called subsets. And we're really lazy in math. We don't like to write words if we don't have to. So this is the symbol that we use for a subset. The notation that we use for a subset. So it is like turning a U on its side and putting a line below it to say it's included in this set. It is a subset. So from the above symbolism, if we go back and take a look at this, we will see that the natural numbers are a subset of the whole numbers. It's inside there. But the whole numbers are also a subset of the integers, and that was set Z. Notice the capital letters that I used up above. Those are the capital letters that I'm going to use to show the subsets. So natural numbers are a subset of the whole numbers. Whole numbers are a subset of the integers. Integers are a subset of the rational numbers. Rational numbers are a subset of the real numbers, which just happens to be a subset of the complex numbers. So all of those link together. Notice how we did not put anything with irrational in there, anything with imaginary, because what we wanted to show here is how deep those subsets go for one portion of the number system that we know. Now, What if they don't have anything in common? What if there are two subsets like irrational numbers and imaginary numbers that really don't have anything in common? There are two separate diagrams up there. There's no overlap between them, and that's called disjoint. So disjoint, telling us they're not joined. If you think about just the English part of this and what's your prefix, and then what is the main word in what we're saying here, and dis meaning not, so they're not together. Now, if they do not have anything in common, they're mutually exclusive. Now, many of you did not take probability and stats, but some of you did, and you've heard that mutually exclusive before, and mutually exclusive just means two sets that have absolutely nothing in common. That's what they mean. So the set of automobiles and the set of dinosaurs. There are no dinosaurs that are automobiles or automobiles that are dinosaurs. So those two things are mutually exclusive. I want you to grab your calculator. If you don't already have that with you, maybe pause this if you need some time to go grab that. But here's what we're going to do. We're going to punch these in, and we're going to take a look at what happens. So if you put 7/4 into your calculator, and you've got your calculator set on floating decimals, that will be under mode. You're going to want to make sure that you have your decimals on floating. What that does is it makes sure that the calculator is giving us the full screen to get us all of the decimals that we want to see. It's actually the, as you go horizontally, it is the second spot down on your mode key there where it says float. And you want to make sure that while blinky, the cursor is over the top of float, that you just hit enter. And that way we're not letting the calculator round at all. We're seeing everything that we can possibly get. So when we put 1.75 in there, sorry, not 1.75, 7/4, we get 1.75. That's it. There's nothing else behind it. It stops. The fancy word for stopping is terminating. So that is a terminating decimal. It quit. That means that 7/4, 1.75, those are equivalent. We could use them interchangeably for the math. Now in here, as in any math class, we'd prefer the 7/4. We want something that's perfect, and fractions are considered more elegant. Elegance in math means that what you're using is a perfect representation. So the 7/4 would be great, unless of course we have a problem where it actually tells us that we are supposed to round. So we plug 4/11 into our calculator, and we get 0.36363636363636. Now to show that repetition of the 3 and the 6, we put a line over the top, and that is known as a repeating decimal. Now, if we saw 0.363636363636, we might not recognize it because 4/11 is not something that you do a lot of math with. But there are methods that you can learn to take a repeating decimal like 0.36 repeating forever, the 3 and the 6, and work backwards and show that that is a rational number because it can be written as a fraction, which is 4/11. Next one down, we've got the square root of 3, and how you're going to punch that in is by hitting second and then the x squared button on your graphing calculator and then the 3, and you're going to see 1.732050808. And at that point, you might think, wait a minute, maybe that's a repeating decimal. But if we put it into a computer and have it generate it, what we find out is, no, it was just happened to be a coincidence right here that we had the 0808 piece. There isn't any repetition. This keeps on going without repetition. It doesn't stop. And so this is an irrational number. We cannot write that as a fraction. To write it as a fraction, we need it to either be a repeating decimal or we need it to terminate, and that is not happening here. So this is called infinitely non repeating. So those infinitely non-repeating things like pi are definitely going to be irrational numbers. And we can sometimes use our calculator to figure out whether or not, hey, this looks like an irrational number or not. But best idea is probably to put it into a computer if you see something like the 0808 that we have repeating at the end here, and you start thinking, well, maybe there is some repetition going on. That's when you would want to check it out with a computer instead, so you can get more than just the 10 decimals that we're going to see. So next up, it says we blank real numbers with a calculator. Calculators do not give us exact answers for irrational numbers, so we approximate real numbers with a calculator. Remember, the calculator response is not always exact, and we're going to work with exact answers. So if we can write something as a fraction, or in this case, leave it as the square root of 3, then that's what we would do. We want to be as exact as we possibly can get. So the calculators will be helpful, but we need to use our brains and figure out what's going on. So let's see what we have here. This says examining decimal forms of rational numbers. Determine the decimal form of, we have 3 rational numbers here. So go ahead and pause the video, punch those into your calculator, and see what you get. This exercise really just wanted to see, when you punch this stuff in, do you understand what you're getting? But I would also ask you to go back and think about the terminology that we just used, and think about how 1/16, that's a rational number. It definitely is a rational number. All of these are rational numbers. You can write all of these as fractions, and rational, root word is ratio, writing them as a fraction. So every single one of these would be in the subset of rational numbers. But when you think about the decimals, our 0.0625, that would be a terminating decimal. Because it stops. And again, 1/16 and 0.0625, those would be equivalent. Our 2.037, 037, 037, well, that would be considered a repeating decimal. We can see that. And then 1/17. When we take a look at that, we don't see a pattern, and it does not appear that that is going to stop. So this would be considered a non-repeating decimal. So we need to know the difference between those. And, be able to pick them out when we see them, terminating, repeating, or non-repeating. So all of those are rational. They can be written as a fraction. The real numbers and the points of a line can be matched 1 to 1 to form a real number line. That's what we want to be able to do, is to represent these graphically, because remember, we're not just going to do things algebraically, we're also going to do them graphically. We start with a horizontal line and match the real number 0 with a point O called the origin. Positive numbers are assigned to the right of the origin and negative numbers to the left, as shown in figure P2. So what you see here is what we need to do to represent things on the number line. Notice they didn't just make the blue dots and walk away, they also labeled them. And we want to label them with what was given to us. If the book says that you are to place negative square root of 3, what you don't do is write down that approximation of negative 1.7320508808. Now we use that to figure out the location of a negative square root of 3, but this would be the label, because that's what was given to us. Same thing with pi. They want us to graph pi. We know it is 3.14 blah blah blah, so that's what we use to position it, but we definitely will label that as pi. So kind of a silly little exercise, but remember that over the summer, some people can get a little twisted around backwards, especially with the negatives. So we want to be able to graph those on the number line. And this says how many real numbers are between 0 and 1 on a number line. And you start thinking at first, well, there's only so many that are going to fit there, but you'd be wrong, because you could say, okay, I know 1/2 is going to go on there. Well, how about if I cut that 1/2 in half, I'm going to get 1/4. All right, well, what if I cut that in half? Now I have 1/8. 1/16th, 1/32nd, 1/64th, 1/128th, and you realize you could go on forever doing this. So those three dots to indicate we're going to continue on infinitely. So how many real numbers are between 0 and 1 on a number line? There are infinitely many between those two numbers on a number line. And we could represent them on a number line graph. The number that we associate with a point is called the coordinate of the point. You know, when we go to graph it, that's going to be the coordinate of the point. So the position that we see on that number line, the number that we associate with a point, is called the coordinate of the point. So let's go back to our objectives for the day. And we had identify subsets of the real number system. All right, so you want to think back and say, okay, it was natural numbers into whole numbers into integers, and just kind of take a look at that. And then our second part of the objective, correctly use set builder and interval notation. So at this point you'd say, hang on, I don't think we've done any of that yet. And you would be absolutely right. But we're building into it is what we're doing. We're building into that objective. So the number we associated with the point was the coordinate of a point. The set of real numbers is definitely ordered, and we can use inequalities to compare any two real numbers that are not equal. 2 is less than 3. Less than is an inequality. So anytime we see inequalities, we should think, okay, we've got less than or equal to, greater than or equal to represent those two numbers. So the order of real numbers we see in this box, if A and B are any two real numbers, A could be bigger than B. And what that means is, if it says 3 is greater than 2, when we take 3 minus 2, we get 1, which is positive. And we just read that off as A is greater than B. Now, 2 is less than 3. Well, 2 minus 3, definitely going to be negative. We're going to get a negative 1. And we would read that as 2 is less than 3. A is greater than B. Okay, 3 is greater than or equal to B. Well, 3 minus 2 could be positive. It could be 0 because it doesn't have to be just greater than anymore. It could be A is 0 and B is 0, and 0 is equal to 0. So we get a new choice here where A is greater than or equal to B. Same thing with A is less than or equal to B. If they're both 7s, 7 is less than or equal to 7. That is absolutely true. Could be 0, but it could be 1 and 7. In which case 1 minus 7 would be negative. So A is less than or equal to B. So just reminding about our inequalities here, and the symbols greater than or equal to, and less than or equal to, those are called inequality symbols. In, meaning not, equality, root word equals, not equals. Now you could argue, well, wait a minute, greater than or equal to, less than or equal to, those have equals in there. But remember, that's one of the options. It could be less, it could be greater, or equal to. So the trichotomy property says, let A and B be any two real numbers. Exactly one of the following is true. So exactly one of the following means the answer is unique. Either A is less than B, or A equals B, or A is greater than B. You get one of those, never all three of them. So trichotomy, we have three choices, and we need to know which one would be the correct one. So inequalities can be used to describe intervals of real numbers as illustrated in example 2, and you should start thinking, okay, wait a minute, one of our objectives said something about intervals, so this is going to be important. So interpreting inequalities, we want to describe and graph the interval of real numbers for the inequality. So describe means put it into words, you know. Kind of the aggravating part of this would be, gosh, I already know how to do this. Well, good. You know, let's all remember. So x is less than 3. X is a variable, and it stands for all real numbers. So all real numbers less than 3. So there's our description. And the graph, what we want to do is show that we understand where 3 is on the real number system. So we wouldn't want to just put a 3 on there and slap it on there, but maybe something like 2, 3, and 4, so people will see what's going on. And when you get to college, you're probably going to have to do this. And that's to say, I'm going to label this number system with an X because there was an X in my inequality. And then what we need to do is figure out, is this an open or closed dot, like we used to do last year in Algebra 2, and say, well, we're not including the 3. 3 is not less than 3. It's equal to it. So open dot on the 3. And then we want to point our arrow in the direction that would be less than 3, and that would be these numbers this way. So that would be the way that we graphed this back in Algebra 2. So why is Cedar Home saying that? Are we going to graph this different now that we're in pre-calculus? Yes, we are. And that's because what we're going to do is we're going to start using grouping symbols to talk about whether or not things are included. Now, the first one I'm going to use here is going to be that half moon known as a parenthesis. But we could certainly, if we need to, go the other direction as well. So parentheses, what that means is we're not including that point. So if we don't want to use the 3, we have to use a parenthesis at 3 to show, you know what, 3, that's our marker right there, but we don't want to include it in our graph. So what if we do want to include it? And what are we supposed to do if we need that? Well, then we're going to need the square brackets. The square brackets are going to show us, oops, forgot a T there, that the point is included. So we're going to use our half moon, our parentheses, if we don't want to include a point, and we're going to use a square bracket if the point that we want to graph is included. So as you look at B, first thing we have to do is they wanted us to describe this. So when we're looking at inequalities that have an and situation going on, what we want to do is think from the middle of the inequality out. So in this case, and this is called a compound inequality, X stands for all real numbers. And now I'll start reading it to the left. All real numbers greater than -1. And that's important. Notice how when we have an and statement, I've always called this an and sandwich. It's like what we have here is between the two slices of bread that we have. So an and statement. So greater than -1 and, now read it to the right, less than or equal to 4. So compound inequality, and in this case this was an and compound inequality. Now to graph this one, we're going to need a few more numbers, and that's because what you need to do when you're graphing on the number line is make sure that your intervals are consistent. If you go back to A, you're going to see that I kept 1 unit between each of the points that I was graphing. So for this one, at the very least, I'd probably want to start with a -2. And go to at least a 5. Because I know that I have to have the -1 on there and I have to have the 4 on there. And now I need to graph what I know from last year. And what I know from last year is that if I don't want to include the -1 because there is no equals bar right here, I have to make an open dot. But I want to include the 4, so that's going to be a closed dot. And here's where thinking of an and sandwich makes this really, really helpful. Because remember, the numbers that we want to graph are sandwiched between -1 and 4. And there it is. So old method, algebra 2 way, that's what we would do. But now in pre-calculus, we're going to do it this way. So I still have that same number line that has those constant intervals of 1 unit. But I realize I don't want to include the -1. There was not an equals bar at -1, so that needs that open parentheses. But I do want to include the 4, so that's going to be a closed bracket at 4, which is a square bracket. And then shade in between. So pre-calc way, going to take a little getting used to, but I hope at some point you will see that it is, it's a little simpler, your whole open dot, closed dot, but some people like to think of it that way, and then just remember open dot is going to be a parenthesis and closed dot is going to be a square bracket. So now, writing inequalities. It says write an interval of real numbers using an inequality and draw its graph. So they have these in the words for us, and what they want us to do is put them into an inequality, and then we want to go ahead and graph those. So go ahead and pause at this point and go through and do A and B, and then you can start the video up again to see what I've got. Quick reminder here that what we want to do is start using the pre-calculus symbols. We don't want to do the algebra 2 anymore. And so for x is greater than -4 and less than -0.5, those would both be using the parentheses. Now you might argue, well, Cedar Home, this has decimals on it. Shouldn't we go ahead and use the decimals with this one? Well, remember that we should know that -1/2 and -0.5 are interchangeable, and it is definitely a plus to show your understanding of those fractions as decimals. And then on the second one, what we want to do, because x is greater than or equal to 0, I don't like that that's kind of muddled together there, would be a square bracket at 0 and then going off to the right forever. So now let me introduce you to something else. And both of those we are graphing x. So at this point we say, all right, I wonder if there isn't an easier way to write that, something simpler. Well, in fact, what we've been doing as we are learning our new way to graphing is we are seeing the new symbolism that we should use. X is greater than -4 and less than -0.5. We can now write this with this symbolism. And that will tell us, hey, we needed to have that open bracket, parentheses, at the -4 and the -0.5, but because this was an and statement, we just need everything in between them, and that's what this comma is going to do for us there. It's going to show us that we graphed from -4 to -0.5. So what do you do with B? Well, you do exactly what you graphed, and you say, this is a 0, but where am I going with it? What's the other end point? There isn't another end point. This keeps going forever, and that's going to be infinity. And we're going to use an open bracket for that. In fact, that was one of the mistakes that we noticed in this textbook. We never use a closed bracket, a square bracket, for infinity. Infinity is an open bracket because it can keep going forever. So those are two very shortened ways that we can symbolize these. The writing of the inequality kind of coming together with the graph itself and making all of that a little bit simpler process as we go through it. So notation, you're going to notice I have a former president up here. That is Richard Nixon, and he resigned before he was going to be impeached. Now, why did I do that? Because the brackets that we're using here, I call those Richard Nixon brackets. And here's why I call them that. Richard Nixon had a very distinct profile, and in this picture it's not quite as exaggerated as it would normally be. But notice that he had kind of a pointy nose. And so when you draw his profile, you get what I call a Richard Nixon bracket. Those are the brackets that we use for set notation. Specifically number sets, but we definitely could use it for other sets as well. You know, if you had a set of triangles, you could use this set notation to show that they are a set. So what we do is we start with this symbol, we list the elements of the set, and then we draw another Richard Nixon bracket on the other side. So ways to represent a set. We could go back and say, gosh, I want to represent that set that we had as M, that imaginary numbers. All right, we could just write M. M is the set of imaginary numbers. That's what we did back on the Venn diagram. We could list all of the elements. Maybe there are only 4 elements in our set. Maybe they're 1, 2, 3, and 4. We could write those. And you never list an element twice. It doesn't make any sense to say, my set is the numbers 1, 1, 2, 3, and 4, because that makes people think you don't understand that 1 is the same number as 1. So we're not going to do that. In fact, let me write this up here in case anybody was busy writing something down. My Richard Nixon bracket is not going well here. There we go. This would just plain be silly. We're not going to do that. So don't list anything twice. We could list enough to show a pattern. Notice in the next set we have 1, 1, 2, 3, 5, 8. Now in this case you'd say, all right, Cedarholm, why is that 1 there twice? Because it makes a difference. In this pattern, this is actually called the Fibonacci sequence. And the pattern for this is you take the 2 initial numbers and add them together to get the third. And then you take the next grouping of 2 numbers and add them together to get the third, and so on and so forth. So the Fibonacci sequence needs that 1 there to get people to be able to understand the pattern as you go through it. So if it's not something that's absolutely a must with the pattern, then we don't list it twice. Now, new kind of notation, and we're going to be using this in pre-calc. Remember, that was one of our objectives, was the set builder notation. So specifying a form or a rule, that is set builder notation. This says for the set of all numbers n is going to be less than 4. That is set builder notation. Interval notation, we're also going to be using that. That was another part of our objective. So set builder and interval notation. And interval notation is what I was talking to you about in the last problem, where we're saying we understand that 3 would be like a closed dot in this problem. 5 would be an open dot, and then we'd need to sandwich our shading in between those two because there's a comma there connecting those. So as we go through this, if you start thinking, well, what if it's not an and compound inequality? What if it's an or? Well, we'll get to that in a little bit, so don't worry about that just yet. So bounded intervals of real numbers. Bounded. It says let A and B be real numbers with A less than B. And we see the interval notation here. And for the first one, we see that it's an interval from A to B where A is included and B is included. So that's called a closed interval. And of course, we go ahead and change that into inequality notation of an and sandwich. And we see the graph. So that's bounded. We have an A and we have a B. Those are the bounds of this graph. Those are the cutoffs, the endpoints. In the next one, we have that A and B again. Those are the endpoints. So it's bounded, but A and B are not included. So that's called open. A and B not being included, that is open. And we see our inequality here does not contain the equals bars. And we see that we're no longer using the square brackets. We are now going to use the parentheses to indicate that. Next one says square bracket A, B, parentheses. Okay, It's not open, it's not closed, it's kind of both. That's called half open. So half open has one of the endpoints included and the other one is not. And our inequality would definitely show that with 1 equals bar as we go through that. Again, the graph is not surprising. You can just go back to the interval notation and see that that matches. And the same thing, kind of vice versa here, where A is not included and B is. Again, that's called half open. So we see 1 equals bar, not 2. And again, the interval notation shows us how to graph. So, bounded intervals. Bounded intervals, the numbers A and B are the endpoints of each interval. Okay, Cedar Home, aren't they all going to be bounded? No. We had an example a little bit ago. That would be unbounded. Right here. Infinity cannot be bounded. You could say, okay, but it's bounded on the one end because it's got a 0, an endpoint for you to stop at. But it's not bounded on the other end. You know, they both have to be stopped in order for this to be a bounded system. So as we look at these, we see there's no infinity on any of these. Sorry, that's the smartboard making a little noise there. We have the endpoints. We have the endpoints for all of those. So next up it says we want to describe the interval of real numbers determined by the inequality x is less than 2. So let's go ahead, because it's said describe the interval, let's use interval notation. And we'd say, okay, we've got a 2. Do we want to include the 2? No. No equals bar. All right. So it says all real numbers less than 2. Well, that's going to be negative infinity. And then we think, well, what are we supposed to put over there? Well, remember, we're not including infinity because infinity can't be stopped. It keeps going. So this interval would be the interval negative infinity to 2. And both of those would be, they say, non-inclusive. They're not included. That's why we don't have the square brackets. So it asks us, is the interval open or is it closed? Now go back to your box up there and see what you think. Open or closed? This one's open. We do not have those square brackets. This is definitely going to be open. So in answer to their question, open. The interval notation. Negative infinity to infinity, and that's just kind of a sideways H. You'll get used to that. At first it's going to be a little clumsy for you, but negative infinity to infinity represents the entire set of real numbers. The entire set of real numbers. So now that I explained bounded and unbounded, it's not going to surprise you to see that in all these unbounded intervals of real numbers, you're going to see infinity. You know, anytime we see infinity, those are considered unbounded. So this box is about understanding that infinity, both positive and negative, mean that it's an unbounded interval of numbers. So now I look at this and think, okay, that's not closed. It's going to go on to infinity forever. But we do have one endpoint, A. That makes it closed. Notice that each of these intervals has exactly one endpoint, A or B. And of course, because we're saying A is the cutoff and then we're going to the right forever, x is greater than or equal to A. And we see that our interval notation is the same as what we have for our number line graph. The second one has A and infinity, but neither one of those are included, so that is open. X is greater than A. And we see that we have a parenthesis there on our number line graph. Next one says negative infinity up to B. It is closed. If we have one square bracket on these systems of unbounded intervals, we are talking about a closed system. So negative infinity to b, which means we're going to the left forever, but we have that cutoff at b, and it is included with a square bracket. And then we see negative infinity to b, but these are parentheses. So that one is called open. All right. So if, when you have an unbounded interval, you're using infinity, if the other endpoint is included, if we see those square brackets there, it's closed. If it's not, it's open. So bounded and unbounded, open and closed, half open, all things that we need to understand about, well, both our set builder and our interval notation, but definitely more for our interval notation than anything else. So quick little synopsis here. I want everybody to write this down. Remember, bounded is no infinity. No infinity. Unbounded will have infinity. It might be infinity, it might be negative infinity. And then think about the fact that with bounded, we could have half open. That was a possibility. But with unbounded, it's either open or closed. So if the endpoint is included, if you see a square bracket, then it's closed. So if we talk about open just versus closed for a second, trying to write small enough so I stay on the page here. Open looks like so. But if we're talking about unbounded, closed could look like this. It could look like this. And closed with bounded would look like this. Do keep in mind that bounded can be called half opened. So the first thing we want to do, it says describe as bounded or unbounded and open or closed, is we need to figure out, is it bounded or unbounded? And we can see infinity in two of these. So you know what? Stop the video for a second and write down what you're thinking about A and B. Bounded or unbounded, and C. All right, so here, with infinity, unbounded, unbounded, bounded. So now we go back and we label these as open or closed. Well, for A, neither one of those endpoints is included, so that's going to be open. And because it's unbounded, we don't say half open. For B, unbounded, it's either open or closed. They are including the 5. It is closed. And then for C, bounded, well, both of the endpoints have to be included, and they are here. So this would be a closed system. Closed interval. Caution when using interval notation. If the interval is open, don't confuse the interval with an ordered pair. That's really important, you know, especially if we're writing these and we say, wait a minute, look at, we've got these nice parentheses on both ends here. Well, if you're talking about intervals, don't think of things as ordered pairs. Interval notation can only be used when talking about intervals of real numbers through a continuum. So all real numbers, which includes, of course, all the fraction portions in between. Interval notation must be written from least to greatest. This is big. You cannot write down 4-9 for 9-4. You can't do that. You want to make sure that you stay with the number line, as if a number line were sitting right in front of you. 9 does not come before 4. We would never write that. So always think number line when you're writing your interval notation. So on the number line, 4 is to the left of 9. That would be the correct way to write that. So we've got our open bracket at 4, and we're going up to 9, making an and sandwich. We are going to include that 9. That's correct. but the other way doesn't make any sense. Not going to receive any credit for that. You have to think number line as you do these things. So now what I'm going to have you do is go ahead and go through example 5, A, B, and C. Stop the video, see if you can get these. It says draw a number line graph and write each in both set builder notation and interval notation. Try and do the set builder notation going back and looking at one of the examples that we talked about earlier. But I definitely can do the first one with you, and then we'll do the A or the B and C portion just to make sure you get the set builder right. So this one says all numbers greater than 4 and less than or equal to 9. So 4, probably put a 3 on there as well. All right, looks like so. 4, think, well, am I including the 4? No, all numbers greater than 4, don't want to include the 4, and less than or equal to, square bracket, 9. All right, so now I'm supposed to do this whole set builder thing. And it's up to you whether or not you want to use an X or an N. I'm going to use an N because this is numbers. So set builder notation, we have that Richard Nixon bracket. We start by saying for all numbers N, and then we make a vertical line. And then we define it, and we say, okay, well, what's going on? Well, if we're talking about greater than 4 and less than 9, we need to have an and statement. So n is going to be greater than 4, reading that off from the center out, and it's going to be less than or equal to 9 on the other side, and Richard Nixon brackets to finish that up. So that's the set builder. And then if we want this in interval notation, all we have to do is look at the graph and say, well, we had a 4 with parentheses, we had a 9 with a square bracket. There's the interval notation. That's why interval notation is so widely used. It's just so much easier. So now that we've gone through an example of set builder notation, I'll feel a little bit better about letting you do B and C on your own. Give those two a try. You might have to look up the temperatures for Fahrenheit for liquid and C on the internet to give that one a try, but go ahead and try the two of them. As you look at your answer for B, there's probably one thing that you just didn't know what to do with yet. As we graph this, we see n is a set of all numbers as we write our set builder notation, such that n is less than 4 or n is greater than or equal to 9. Notice this is not an and sandwich. We did not graph between the two. We did not want to include the 4, but we did want to include the 9. So then when you go to do the interval, you're saying, well, this is going out to negative infinity forever, and it's stopping at 4, and we're not going to include that. And then this is definitely including the 9, and it's going to infinity forever, but what on earth do I put in between those two? This is new. Well, what we do is we use the union symbol, and that's just a big U without maybe the fancy line that you learned to do back in elementary school. So we've got our U there, and that says union with. So we've got our negative infinity to 4 in union with 9 to infinity, including the 9. In C, if you look this up, you know that in Fahrenheit, water is going to be liquid between 32 degrees and 212 degrees. So obviously I wasn't going to put every little interval as I go through that, and I can see my parentheses off a little bit here. There we go, right through that 212. So this is an and statement, but between 32 and 212 degrees Fahrenheit is when we're going to get liquid. So now on the bottom part it says rewrite each interval notation as an inequality and graph on a number line. So this is backwards. This is take what they give you and do it the other way. So for A, we're going to write that as an inequality. Same thing for B. But then for C and D, write those as intervals and then go ahead and do your graphing. So again, I'm going to stop for a second. You stop the video and see what you can do with these. So let's see what you have. In A, we're saying we have closed bracket at -6, open bracket at 3. So we want all of the x's or n's, it depends on what you use for your inequality here, that are greater than or equal to -6 and less than 3. So closed bracket at -6, which is our square bracket, and open bracket parentheses at 3. For B, we have from negative infinity to -1. So in this unbounded situation, we want to go out to the left forever. We do not want to include that -1. So that's definitely unbounded and open. Looking at C, we write that in interval notation, which would be a closed bracket at -2 and a 3, and that's because both of those do have an equals bar, so we want to include that. And then we graph that. In this case, we've got the old Algebra 2 way because it was written in the old Algebra 2 way when we started. Now we go on to D. And D is from 4 to 9, but we don't want to include the 4, so we use the parentheses there. Close bracket at 9, we are going to include that, and we graph that. Now, pause the video again and see if you can label these as bounded, unbounded, open, half open, closed. Well, with A, we see this is bounded. There's definitely no infinity going on there. And one of the two endpoints is included, so this would be considered half open. Looking at B, we see that we have an unbounded because it definitely has that infinity going on. And because -1 is not included, this is going to be open, so unbounded and open. You look at C, and you see definitely bounded. We have our two endpoints, -2 and 3, and this is definitely closed. We did include those two endpoints. And then for D, we don't see infinity here, so that means this is bounded, but only one of the two endpoints is included, so this is a half open. And again, that's just to remind us that that's just part of our objective, is knowing all of that good stuff. So on the next page, we have AND, which has the set builder notation for us. N is greater than 20 and N is less than 60 for the all sets of N. Interval notation from 20 to 60. So we have to use less than or equal to. Notice it would not be okay to switch the positions of these two numbers and switch those two signs. That is not okay. We must write these in terms of a number line. And the number line, as you look at it, is always going to be smaller to the left and bigger to the right. So that's how we have to write it. These are the no-nos. Can't do that. Can't do that. Absolutely do not make those mistakes. In fact, don't even write those two down. Do not switch them. Must be in terms of the order on a number line. I always remember my 5th grade teacher had an integer number line right above the board at the front of the room. So even though it's not there today, I see it when I look up there because it helps me remember the orders that I have to put these things in. With OR, we have our set builder notation that says for all M is going to be less than or equal to -5, or M is going to be greater than or equal to 3. Here is that union symbol that we need with these. So instead of the word OR, we use that union symbol, which is that big U. But once again, you don't put the 3 on the left and the -5 on the right. Again, don't even write these two down. The -5 is definitely to the left of the 3 on the number line. You have to keep that order. It will be marked wrong in pre-calculus if you do not do that. It's just one of those college things. You're going to get points taken off if you do this stuff, and we don't want that. So example 7 says write these in both set builder and interval notation. So A says the set of all n that are less than 3 and greater than or equal to 7. All right. 2, 3, 4, 5, 6, 7. I want to give you a visual here so we can think about what's going on. This says we want the set of all n that are less than 3 and greater than or equal to 7. Uh-oh. Problem. And means we need the stuff that's between those, the things that are double shaded. We don't have any. So what do you do in set builder notation if you want to tell people that it's the empty set? Well, you make the Richard Nixon brackets and you don't put anything inside. This is an empty set. There are no numbers that are less than 3 and greater than or equal to 7. Doesn't happen. Well, what do you do in interval notation? Well, you write the empty set. And the empty set is a computer version of 0, which would be a 0 with a line through it. That's how we signify the empty set in interval notation. For B, this one says the set of all x between -6 and -15 inclusive. All right, so to graph that, I'm not going to take the time to write all of these down for you on this one. We say, hey, it's the x's between these two. Should I include those 2 points? Yes. It said inclusive. And since they didn't get more specific and say inclusive of -6 and non-inclusive of -15, that indicates to us that they are both included. Now notice in this problem, we put those backwards, and that's to try to trick you when you're doing your writing. So your set builder notation, they said they wanted us to use an x. So for all x, we need an and sandwich. To show x is greater than or equal to -15 and x is less than or equal to -6. For our interval notation, very easy. We can just think about our graph over there and make sure that we have closed brackets and that the -15 gets written down first, because -15 is to the left of the -6. All right, let's see what you can do with example 8. This is kind of a challenge problem. There's a lot going on here. So go ahead and pause the video and see what you can do. In case you're struggling with these, because there's a lot more going on with these too. We look at this set and we say, okay, so I've got a little and action going on here. I have an and action going on here because I'm shading in between those two, but this is an or. And that is what determines how you're going to write these inequalities. So the first portion of this one would be saying to yourself, okay, what's going on as I read this from the left? What's this look like? Well, I need from -3 to 2. So and between -3 and 2. So I have to write it as n is greater than or equal to -3 to include that -3, and n is less than 2. Next portion would be right here. Well, that's another and. But you can't include the -2, so the portion that we need here, oh, forgot my little negative, is an or, to say, all right, it's this, or it's n is greater than -2 and n is less than or equal to 0. But now we've got another break. And that little break is definitely an or. So either those first two things are taking place, or n is greater than 1. So that would all be on one horizontal line. I just can't fit it up here and leave myself room for B. Much easier is the interval notation. Look what's going on down here. From -3 to -2, closed bracket on the -3, but not on the -2 because that dot was not shaded in. Union with from -2 to 0, but the -2 is not included. The 0 is. Union with 1 to infinity, where that is unbounded because the 1 is not included. So not only are there compound inequalities with and statements in this one, but there are also some ors. So again, go ahead and pause the video and now try B. We've got the same things going on here with B that we did with A, where we have to think, okay, how am I going to represent what's going on here? And then I'm going to have to write an or. You know, I've got a piece taking place as I go out from -4 to the left forever. And then I'm going to have to figure out how to write that, which would be an and statement because we're shading in between, and put another break in there, which is an or. -1, that's the part where you probably said, I don't know how to do that. We didn't do one of those yet today, and you are absolutely right. And then we've got to have another or, And then we have to have another and. So lots of ors and ands with this one. So we start at the left and we say, all right, set of all n such that n is less than or equal to -4. Yep, that's taken care of. All done. Or, because there's a break. Well, now we need from -3 to -2, but we want to include the -3, and oops, I see I put a. This should just be less than right there. So n is less than -2. All right, that portion. Done. Now, how on earth do you do the -1? Well, just like this. You say n equals -1. And then you have another break in it. So that's an or. And then we have the and statement to represent the last one. And good grief, I got carried away with my equal signs on that. That should be n is greater than 0 and n is less than or equal to 2. So that would be set builder notation. So what do you do with interval notation? Well, we're going from -infinity to -4, including the -4, because it's a closed dot up here. Union, there's our or. -3 to -2, but don't include the -2, so we have a parenthesis. Union with, how on earth do I write -1 in interval notation? Just as a -1. And that's a union from 0 to 2, where 2 is included. I'm going to stop this and fix. That's driving me nuts that I had those equal signs all over the place. All right, that's better. Had to fix those up. And again, anything with those closed dots, we have the equals bar. Anything that has an open dot does not get the equals bar. So that meets our objectives for today. If we go back to the objectives page, we see that what we were trying to do is identify subsets of the real number system and correctly use set builder and interval notation. And I know this video went long. Usually what we will have to do is pick up a little bit of this in day 2, but since you'll be doing those 2 assignments together anyway, I really didn't have any fear that you'd stop using the video partway through this. So at this point, what you need to do is say, phew, we have those 2 objectives all taken care of. So now what do I do? Well, you're going to write on your paper that this is pre-calculus. This is lesson P1, day 1. And you're going to write the page number down. Pages 9 and 10. And what you need to do is numbers 1 through 21, all, 22 to 28, just the evens, and then 30 to 40, all. So when we don't put odd or even behind something, that's because you have to do all of those. So 1 through 21, all, 22 to 28, just the evens, and then 30 to 40, all. And I know these will go really fast for you. Those last 2 problems that we did, that really is over the top from what you're going to have to do in your homework. So go ahead and work on that. And again, check your answers. Make sure that everything's right. Odds in the back of the book, evens from my website. Try the frequently asked question videos. Not sure there was one for this section. I don't think anybody had any questions that they needed me to put on video for them. When they looked at the answers, they figured out what they had done wrong. But welcome to pre-calculus, and I hope you're feeling like a lot of today was review, a little bit of new learning.